Okay, well, good morning, and thanks to the organizers of this workshop to give me the chance to give this talk. So, reducing noise by converting and combining gradient components. I'll start with this graphic, which is a picture we put together to explain to people what we mean by full tensor noise reduction. So, the converting and combining. The FTG produces 5 gradient components. And then when you have these 5 components, you have 5 ways of calculating the component you're interested in. So we're taking the TZZ. Here's a directly measured TZZ. And then with the 4 others, it presents us with 4 alternate ways of making TZZ. And now we have 5 versions of this thing in hand. And that allows us to do a stacking process. We do a weighted sum. And we get a noise-reduced version of that component. So the outline of what I want to talk to, there's 3 parts to this presentation. I'll first talk quickly about the mathematics of Fourier domain processing. I'll show the application of that method to real FTG data. And I want to discuss the implications of all this for comparing gradiometer designs. So the great thing about working in Fourier domain is that calculus becomes algebra. Derivatives become multiplications, and we can calculate the tensor component from the gravitational potential just by multiplying by the appropriate S function here, which is a function of wavelength, of wave number. And when we do that, we're measuring these, I'm leaving them unknown tensor components. We calculate the potential from each one, and we do a weighted sum of those versions of the potential to produce a noise-reduced version of the gravitational potential, which we then multiply by the appropriate S function to get the component we're interested in. And it turns out if the noise in the T's is uncorrelated, we can write down the optimum weight functions as the square of the absolute values. So if we apply this to the horizontal partial tensor gradiometer, we can write down an expression for calculating TZZ if we have the Falcon components. And this is the same as the expression they actually use, even though it looks very different. I have shown it is the same thing, which is good, otherwise it would be confusing. When you have the FTG now 5 outputs, so the expression gets longer. Yeah, I was glad when I found out they're going to be wide format slides because I can make my equation bigger. So it's really just the sum of these things. There's a wrinkle when you have FTG data because you don't expect the T's to be uncorrelated. What you expect is the gradiometer outputs to be uncorrelated, and the T's are linear combinations of them. But the only consequence of that is you have to add these constant R factors in front of each term, and I forgot them on the bottom, but it's right in the paper and it's right in the code where it really matters. So you can use Parsifal's theorem to estimate the strength of noise reduction you expect, and it varies between the different gradient components. For TZZ, it works out at 1 3/4. For XZ and YZ, it's about nearly a factor of 2, and for the curvature components, it's more than a factor of 4. Now, in the paper, I've tried to write about this in some detail, and I'd really be very happy if someone could reproduce these results. You know, you're taking these numbers from a guy who works for a company that operates a particular kind of design, but I have put everything in the paper that should allow these results to be reproduced. So moving on to the real data. This is probably familiar to a lot of people. It's the survey in Vinton, Louisiana that we did when we were testing gradiometer equipment. Because of that, it doesn't belong to anyone except us. So this is before and after pictures for the TZZ component. This survey is characterized by this big positive anomaly in the middle due to shallow salt and the associated cap rock, and that's associated by a lower negative density anomaly from the deep salt. And you can see before and after the full tensor processing that we've obviously reduced noise, and we're starting to see features that weren't visible before. But that's the vertical gradient. When you look at the curvature components of the FTG, the full tensor processing is the whole game. That before and after, before we just got not much at all. After you've got clear delineation of the classic quadrupole pattern in TXY. And for its symmetry brother TUV, you got the classic plus sign. So for the lower amplitude gradients, the full tensor noise reduction makes a massive difference to the signal's noise. And here's for completion, the horizontal components. Now we quantify what's going on by looking at the spectra and the amplitude density function. Square root of the PSD. So before and after. Before, we have a pretty flat spectrum showing really the dominance of noise with just the signal starting to creep in. These are the curvature components. Then after, we see the slope, that characteristic of the signal being revealed. And what's useful about this survey is that we have this shelf here representing a white noise floor forming. Now, we don't have a way of measuring noise in fully processed full tensor data. It'd be a very useful breakthrough if we did have one. But what we can do is we can estimate the noise that is present. And there's two ways of doing that. One is by simulation. What we do is we take this white noise level here and we run it through a simulation of what's involved in the processing, including the cutoff wavelength that was set at 250 meters here. I should say that line spacing in that survey was 250 meters with a swath in the center that was half the spacing. So it's the cutoff based on the line spacing. And the simulation, the green line, predicts this noise level just a little bit above 1 e/kilometer. And that corresponds to the small section of white noise shelf that's present in this data. And the blue line is an estimation method based on the before minus after difference. And this is actually similar to the method that was published in Geophysics by Martinez and Lee just this last issue. I think it works well when you're looking at PSDs. And what you do is you look at the spectrum of what is removed, and then you rescale it based on what you expect to be left. It gives you an estimate. And what I want to point out about this is it comes at about the same level, and it's nice and flat, indicating that the stuff that we removed looks a lot like white noise, which we really hope it does. So that was the curvature components. It's easy. We expect the noise level to be higher by about a factor of square root 8, and that's what we're seeing. Rather than being just above 1, we're just around 3 on this. And you see in the vertical component there was more signal present in the unprocessed, just as we could see from the maps. Okay, the third thing I wanted to get across is that this mathematics of what the processing could do for you has to be considered when comparing the gradiometer designs. So these are the two current systems coming out of Lockheed Martin. They're built in the same factory and they both share a very similar platform. So what we have is two strategies for filling this volume with gradient sensing material, gradient sensing instrumentation. And the two strategies, the FTG one is to put 3 sensors in there and orient them at an angle from the horizontal. And the Falcon strategy is to fill that space with one big one and keep it horizontal. So 12 accelerator accelerometers versus 8, 6 channels versus 2. So applying the Parseval theorem analysis to the Falcon data as well, we come up with these numbers. That this is the well-known result that when you calculate ZZ from Falcon, you double the noise level. For XZ and YZ, it's a square root of 2 increase, and for XY and UV, they actually get a reduction in noise about the square root of 2. What I find interesting about this is that the ratio of the ratios is the same no matter what component you're looking at, and it's the same whether the Falcon actually measures it or not. So there's a lot of assumptions. This is a model. I mean, it's physics. You build a model, and then you see how well your model fits reality. There's a bunch of assumptions. The big assumption is that everything's uncorrelated, that all the noise is white. And also we're assuming that actually measuring the component doesn't make any difference. This is the same numbers, just in more dramatic form with green and red arrows. And what I've done is simulate the noise level with random numbers, but superimposed the actual amplitude for a spherical source. So just to illustrate something about the signal and noise, that the FDG measures these large signals, and then when you calculate a component that has a smaller amplitude, you shrink down the noise. And conversely, the Falcon measures components that have a smaller signal amplitude, and then when you calculate something big, you have to expand the noise. And for a fair comparison of raw data, you have to consider the mathematics of the processing. So this is the raw data for this, the FDG raw data for that Vinton survey. These are the 6 gradiometer outputs. You see that one was much better than the other two. The black dotted line is the inline sum, which is the built-in noise estimator that comes with the FDG. So you say, oh, the inline sum's about 6 e-root hertz, but you have to consider the factor of 3.04. And when you do that, you get this line, which is the adjusted inline sum. And this is the equivalent Falcon spectrum. So if you had a Falcon and you was flying Vinton, this is where you'd have to be to get the same thing, assuming all the processing works perfectly. And that comes in at 1.7 e-root kilometer. And then you get an extra square root 2 when you do the processing to get the 1.2 e-root kilometer that we were seeing in the previously. So summarizing the 3 things I want to tell you. That the 5 independent components of the FDG can be stacked in Fourier domain to produce a noise-reduced product. And this theoretically expected level of noise reduction can be achieved with real data. And the mathematics of this processing is a key thing to take into account when comparing gradiometer designs. Okay, well, thank you for your attention.
Okay, we're running a little early, but that's fine. Our next presenter is Mark Dransfield, who almost does not need an introduction. Oh yeah, that's right, I'm doing your trick. A little bit of Australia. Okay, next presenter is Mark, who's going to talk to us about equivalent source and Fourier transform techniques in Falcon AGG data. Mark is 31 years in AGG and was involved very much so with the commercialisation of the first AGG system for exploration. He's published many papers, which I'm sure most of us have read, and presented many conferences. The Falcon team won the CSIRO Research Medal and the ASEG Graham Sands Award for Technical Innovation. So, you know, this is a heavyweight here in AGG.
This is not the bio that I gave him.
Mark experiences includes, now this is a lot here, instrument development, data processing development, interpretation, operations training and management. And Mark is currently the technology manager for CGG or /NEOS Multiphysics. All right, let's get this going. That's not it. That's it. to you.
Thanks very much for that introduction, Theo. So I want to start out by saying that this is, I'm not the lead author on this paper. Tianyu Chen is the lead author here, and he in fact did most of the work. Unfortunately, Tianyu couldn't be here today, so he's volunteered me to speak on his behalf. Bill Drawing did most of the software development in recent times associated with this work, and really all I did was just toss in a few ideas and agreed to come and give the talk. So luckily for me, James has already introduced a few of these ideas. With Falcon systems, we measure the NE component of the gradient tensor and the UV component, and we measure it in two separate gravity gradiometers inside the same instrument, the A complement and the B complement. And in order to make those results as useful as possible, we need to transform that data into all the components of the gravity gradient tensor, particularly the most important, the vertical gradient, and also the gravity field. So this talk is about comparing two different methods of doing that. The first method is the Fourier transform method, as I said, somewhat similar to what James has already talked about. And the second is an equivalent source method, which has been mentioned by other speakers earlier. I'm going to briefly describe those two processes, and then I'm going to talk about how we did the comparison, which is via a model simulation, and then report the results for that modelling. Okay, Fourier transform method. Luckily, because of James, you're all familiar with the mathematics here. So I don't need to dwell on it. We rely on Laplace's equation, and we end up for the gravity gradient with this equation here, which is that the Fourier transform of the gravity gradient tensor is this tensor multiplied by the Fourier transform of this complex function made from the two measured components. Quite similarly, the gravitational acceleration vector, its Fourier transform, again there's a kernel function which is a vector multiplied by the same Fourier transform. I'd like to just briefly acknowledge that this whole idea was developed by Maurice Craig and David Boggs from BHP Billiton back in the 1990s. It's been enhanced and worked on since then, but the original work was by Maurice and then David. So just as an example, here's the vertical gravity gradient, and it's the inverse Fourier transform of this kernel multiplied by the Fourier transform of this complex measured function. And similarly for the gravity, inverse Fourier transform, this particular component from the filter kernel multiplied by the same Fourier transform of the complex measured function. So that's the key step, I suppose, of the Fourier transform method. But the Fourier transform assumes that the data are measured on a horizontal plane, and generally speaking, that's not what we do. So in our implementation, we use piecewise upward continuation and bring all the bits up to a common horizontal plane. We perform our transformations, and then we need to put them back where they came from. The thing is that downward continuation is an unstable process, and so we have to introduce another filter at this stage, a downward continuation filter, to avoid any instabilities as we move the data back down again. And that filter length is typically the maximum of either the survey line spacing or the range of altitudes. So you can imagine if you fly a survey where the altitude of the aircraft is varying enormously, then the filter length is going to be long and you're going to lose some resolution from the survey data. So the Fourier transform method is very fast. It turns out to be accurate over gentle to moderate terrains, but much less useful over rugged terrains where you've flown an aggressive drape. Okay, so onto the equivalent source method. Very simply, this is a method originating from a paper by Dampney. Two-step procedure. You take the measured data, you do an inversion to some equivalent source, some surface of densities. Once you've got those densities on that surface, you can then do the forward calculation to calculate whichever components of the gravity you want. The particular implementation that we use was developed by Rob Ellis, again BHP Billiton, and again quite a few years ago. So we specify an equivalent source layer at the desired depth. Typically that's roughly the surface of the Earth, sometimes a little bit below that. We then invert the measured G&E and GUV data to get a smooth density model which reproduces the measured within some specified errors. And then we calculate from that density model the gradient components and gravity itself on some output surface, which is usually the flight surface. There's nothing fundamental in that produces any limitations based on the terrain or the drape, which is its advantage. However, setting up an inversion requires a great deal more care. You've got to get the parameters to control that inversion to work well in order to get optimal results. Sometimes that means you have to run the inversion several times. And it takes much, much longer to process the same data set compared to the Fourier transform method. Okay, so I'm going to start off by just talking about the areas we studied. But what we did was we took 4 real survey areas, A to D, where we'd flown actual surveys. So this is the size of the survey area, this is the line spacing, this is the average ground clearance that we flew. This is the mean slope of the terrain, and you can see straight away that one of these stands out. This is the aircraft that was used, and this is our sort of classification. So for us, a slope of more than 4 is already considered serious topography. So a slope of 30 is very extreme. Just to give you a little bit more of an idea, these show you the digital terrain models over those 4 survey areas, and this is profiles from a single flight line. The black is the digital terrain model, and the blue is the flight height from the actual survey. And you can see, this one is ranging from more than 1 kilometre, so is this one, whereas these gentle areas are more like a couple of 100 metres. So for each of those areas, we ignored the gravity data that was collected and constructed our own gravity gradient data using models. And this shows you the models used for area A. So there's a cylinder here, a rectangular prism here, and a flat plate down here. So these models are placed in the same survey areas as the real surveys, same flight lines and so forth. And we can calculate through modelling just the components of the gravity gradient tensor, so the north components, east components and the vertical component. We also calculate GUV, which is just half the difference of these two, and the vertical gravity. And of course the G&E and the GUV are the 2 components that we actually measure. We repeated this process for all 4 of the survey areas, but I'm not going to show you all of the models just because it takes a bit longer, but they're all in the published paper. So the G&E and GUV components we added noise to. And for each survey area, the amount of noise we added was the amount of noise we actually measured from the survey. So again, as much as we possibly can, reproducing what happened on the actual surveys, but in a way that allows us to know what the truth should be. So here is the example for Area A, which was flown fixed wing in gentle terrain. The G&E and GUV data after the addition of these noise levels and after filtering at the same filter cutoff that we used on the actual survey. Okay, so to run through the procedure, we added noise to the model data to get us our simulated measured data. Fourier transformed that to give us the tensor and gravity. Used the equivalent source process to give us the same things. And then each of these outputs was subtracted separately from the true model without noise, from the noise-free response. And then we look at the differences in pictures and we look at the statistics of the differences. So this is Area A, and here we're just looking at the vertical gravity gradient. So this is the model result. Here is the output from the Fourier transform method. Here is the output from the equivalent source method. And this is the difference between the Fourier transform and the model, and the difference between the equivalent source and the model. So, two things to point out here. It's not obvious from these pictures, but the random noise in the two is actually pretty similar. You can see the equivalent source output, there's a slope in the difference as well. And that slope comes about simply because gravity gradiometry doesn't reproduce wavelengths longer than the survey area. So in our normal data processing, what we do is we conform our data with some external regional gravity data, or nowadays with the SGrav data that Chris was mentioning in his talk. We didn't do that for this paper, so that slope is not really relevant to our results, but nevertheless you'll see it. In this case, you can see it in the equivalent source data. In one of the other examples, you'll see it in the Fourier transform data. It's not peculiar to either of the methods. So we did that work for all of the tensor components and for gravity, for equivalent source and for Fourier transform. I'm not going to show you all the pictures because obviously there'd be quite a lot. But what I want to draw your attention to, this is Area A, just looking at the standard deviations of the differences. And what you can sort of see is this pattern of a sort of high value, low value, high value, low value, high value, low value, high value, low value, as we go from Fourier transform to equivalent source. So in every one of these cases, the RMS difference between the result and the model is lower for the Fourier transform result than it is for the equivalent source result. So the Fourier transform is actually performing better for this particular model. So this is Area B, and this is again a fixed wing but in severe topography. And now you can see something a little bit different. Firstly, you can see some striping going through in here in the Fourier transform result, which you don't see in the equivalent source result. And secondly, you can see there's a lot less short wavelength information in the Fourier transform than there is in the equivalent source result. And that is pretty much as we expect, because we expect the Fourier transform method to have troubles once the range of altitudes becomes larger. Area C, now we're flying in a helicopter, but over gentle terrain. The Fourier transform result is here, the equivalent source result is here. They look pretty similar. The differences between them look pretty similar, except this time, as I advertised earlier, the Fourier transform result has got a slope in there. Again, that's not germane to our study. That's a result, a natural result that can happen in gravity gradiometry, which we correct for with externally derived gravity. So don't worry too much about that. Then finally, area D, where we're flying the helicopter in a very extreme terrain, following the terrain very, very closely. And here's the Fourier transform result, here's the equivalent source result. So quite a bit of difference between the two. And as with our previous rugged terrain result, the Fourier transform has lost spatial resolution, but it also has lost some accuracy. So we did these models we looked at these differences once again for all of these models for all of the components of the gravity gradient tensor and the gravity data as well. But I'm just showing you the vertical gradient results because they illustrate the result of the study. So in conclusion, generally speaking, both the Fourier domain method and the equivalent source method work well. I haven't here, but it's certainly the case that the Fourier transform method is much easier to set up and requires much less CPU time. Typically for these studies, the order of minutes to run. However, as we've seen, in high terrain relief and highly variable drape surfaces, the Fourier transform results are quite poor. The equivalent source method is much less limited by the terrain or by the drape. It does require a lot more care setting up, and CPU times can be days to run on a survey. So if you have to run it several times because you've got the parameters wrong, then that's obviously not much fun. So the Fourier transform method gave us the best results in areas of low terrain relief and relatively low drapes, but the equivalent source gave us the best result in areas of severe to extreme drape. And that's it. Thank you very much.
Okay, we've got a slight change to the program where we're moving on to John Paine. John Paine was going to be giving a dual presentation with Mark Gruzic, but I think Mark drank too much Adelaide water last night and he's suffered an allergic reaction. He's at the doctor's right now. Now, John didn't love maths or computers until he went to University of Wollongong. And then at the University of the ANU, he learnt how to combine those and research. Now, after roaming the world, this is what he's got here, roaming the world on postdocs for a couple of years, a free spirit here, our young John, landed a job here in Adelaide. And he's learned how to apply all that in the real world with David Boyd. John's been lucky enough to work as a consultant, and I've worked with John, or I've known John for 30 years now, John. Jesus Christ. Bloody hell. And has gained a lot of knowledge and experience along the way. He also, and this is cute, he also loves living in Adelaide, despite the water, and walking in the hills, and going to the markets for breakfast. You took me there once, when we were talking. So now John is going to be talking about an investigation on the effects of filtering in the analysis of AGG data. John.
Except that's not my talk.
It's a good talk though, you did it again.
Oh, well. I wouldn't give it as well, though. Right, here we go. What do we do? I guess there's a presentation down here somewhere that looks like mine. An F5. I've learned something in the last few days. So a lot of the emphasis in the talk this morning and previously has been talking about the actual instruments, reducing noise and the need for that, and it's obviously clear. 10 orders of magnitude is just inconceivable. And then also in terms of the data processing, what's collected from the instrument then has to be massaged in terms of delivering a final product to the client. So this is where I came in terms of Rio Tinto is obviously developing the VK1 system. Well, what they want is not just gravity gradient data, but targets. So that has to go through the normal processing stream of typically inversions. What my particular thing of looking at the data was, well, what's been done to the data after it's come out of the instrument and been processed by the particular contractor and delivered to the company in order to get the best amount of information out of that in terms of the geology and in terms of targeting. So the first thing we looked at was, here's an outline of the talk, is data acquisition. How does the signal change along the flight lines? How's it recorded into the final database that's delivered? And what's the effect of the discrepancy between the data that's actually recorded and the data that's delivered? And in terms of the data modelling side of it, what impact does that have on the terrain correction? Because the terrain is obviously the largest influence on gravity and gravity gradient data, and then how that affects inversion. So the first thing to remind ourselves is that how does the gravity gradient instrument collect the data? Well, it flies along a flight path and obviously records the gravity gradient information along the flight path, but how does it actually take that information? Well, they're not instantaneous readings. We're used to instantaneous readings from MAG surveys. They're not quite instantaneous, but they're near as. So we don't have to consider what happens in the instrumentation in terms of taking the actual reading coming out of the instrument and the actual data that's delivered. It's not like radiometric data or even EM data. They're all windowed data sets, and we're comfortable with that. We're not so comfortable in terms of airborne geophysics in the sense of MAG inversions, where a lot of the processing has come from. So is it an instantaneous reading? Well, if it was, then the field would vary along the flight path, something like the blue line, as opposed to the actual point samples represented by the red line. But what happens is that the output value is actually representative of the signal over the acquisition interval, typically a second. They're just nominal unit distances along the flight path here. So when the plane is flying along, it's actually averaging over the orange boxes and then reporting a value which are represented by the blue dots. So the blue dots, this is only a schematic, the blue dots can actually be quite different to the actual point samples of the actual underlying gravity gradient field. So to really take advantage, or to get the most information out of the data that's being delivered, you also have to incorporate the same processing that's applied to the data in terms of the delivered results. So this is where I get a little bit confused. So in terms of the terrain effect calculation, you can see that the blue dots represent the 1 second samples, 50 metre per second flight path. So you can calculate the response at closer intervals along the flight path, or you can interpolate the position between the known locations. So in terms of, you can average the windows over each of the time windows, or you can integrate the terrain effect over those windows, and both ways have been explored in the literature. The particular, the particular aspect that we'll be looking at is more in terms of saying, well, the instrument generally averages in some form, whether it's a low pass filter or an actual boxcar type filter. So it actually averages over the typically 1 second interval, and that's what we'll be concentrating on. But one interesting aspect in terms of knowing the flight path itself is, well, how accurate is the measurement, the GPS accuracy along the flight path? And you can see here that this is a study that Mark was involved with. The post-processing of the GPS data shows that you've got sub 10 centimetre positional accuracy. So in terms of the actual flight path itself, we can be fairly confident that we're getting a pretty close approximation of where the measurements, or the flight path measurements are actually taken. And the RMS is typically less than 0.1 ertvoss, and peak to peak is 0.7. So in terms of the targeted 1 ertvoss accuracy for the VK1 system, then that's quite manageable. So in terms of the effect of the variations in the flight path, so these are 14 actual repeat flights that have been performed over the RJ Smith test range. You can see that the topography is fairly moderate, but there's a fair amount of variation in terms of the flight paths there. And in terms of the model VK1 response, VKA response, you can see that the peak amplitude over that topographic high, which is something between 400 and 600 ertvoss. So you can see that the terrain has a large effect, and also the variation of the flying height has a very large effect as well. So these are not insignificant values that we need to take account of. And there's a example there of just the variations in terms of, again, this is modelled, just what the spatial filtering, the model terrain correction looks like, and the effects of the filtering are going to vary similarly. Just in terms of the actual components that are being measured, you can see here that there are plots of along that flight path of GZZ, GNE, and also VKA. And you can see that the VKA is actually larger in amplitude than the GZZ. And that comes back to James's comment about the errors actually increase when you take the Falcon components, GNE, GUV, and then calculate GZZ, simply because you're looking at a larger amplitude component. And the VKA system actually is larger again than the GZZ component. So you can see that it's a factor of 4.3 from the GNE, from the GUV, and 4.1 from GNE, which is a bit more than 3. What did James have? 3? Yeah. So I guess that this is specific to this particular flight path and this particular DTM. That's to VKA rather than GZZ. So GZZ is the blue one rather than the VKA, the green one. And there's also a VKC component, which is the cross-line component. But I think the VK1 system's going to fly pretty much in VKA configuration. So that's the long line component. So here's the cowering test range, and just the synthetic, it's a synthetic survey, sorry, which we set up just to test the effects of the filtering that's applied to the gravity gradient data. And we've highlighted the line 38 here, which is the one that goes over this very high topographic peak, which is just barely noticeable in the photographs that I've seen. And set up 2 drape surveys representing sort of helicopter survey, so flying at a lower drape, and a fixed wing survey flying at a higher drape. And you can see that we're just taking a 40-metre drape and an 80-metre drape relative to the DTM in green. So if we look at the effects of saying, well, okay, if you look at the point evaluation of the terrain correction and then compare it to what the instrument would actually measure as it flew along those drape surveys, integrating over 1 second intervals, then you can see at the 40-metre terrain clearance, you're getting errors, differences between the point and the integrated samples at something like 60 ertvoss in GZZ, and also at the 80-metre clearance, you're still getting quite significant variations of 25 ertvoss. Not sure whether they're RMS figures or peak to peak. Anyway, you can see that there are significant effects significant differences between the point samples and the integrated samples. So in terms of doing terrain corrections, clearly if you use the wrong values in terms of if you're delivered data which is integrated, then you also have to apply the same integration to the terrain calculation itself in order to get the corrected data correctly. So if we look at the actual terrain response of the RJ Smith test range, you can see that the GZZ and the VKA look very similar. That's because the VKA is dominated by the GZZ component as opposed to the GXX. And these are the two Falcon components, the GNE and the GUV. And you can see the amplitudes, they're minus 110 to 210 for VKA and 35 and 40 for the GNE GUV. So the question, so in terms of the whole survey, we calculated again the point evaluation of the terrain correction and compared it to the integrated terrain corrections, and just plotted them up as images so that you could see what the variation looks like. And you can see that the ranges, they're all on a uniform -5 to +5 scale. So most of it is fairly green, but you have these blue and red with white peaks variations at locations that are obviously related to the topographic variations that the survey has flown on. Again, you can see that there's more character in the GZZ and VKA than in terms of the GNE, GUV. That's simply because they're lower amplitude measurements that are being compared. So the VKA is the one that we're particularly interested in because that's the system that Rio Tinto is going to be flying. So the question is, well, okay, we can look at the terrain corrections and say, well, what impact does that have in terms of our geological interpretation of data that's delivered? Because obviously when you get data delivered, the major component is the terrain, and that's corrected for, and then you deal with the terrain corrected data in terms of trying to interpret the geology. So in that process, if you apply a point correction to the terrain calculation as opposed to the measurements which are actually integrated, then you introduce an error, which is obviously one that we can deal with. But if you don't incorporate that, then there's a difference between the data that you're inputting into the inversion, which is observed data, the terrain corrected data, but then you're introducing an error because the terrain correction you're applying isn't correct. You're using a point rather than an integrated sample. So it's difficult to sort of take the errors in the previous plot and relate it to, well, what impact does that have in terms of our interpretation of the geology. So we simply took the expedient of inverting the difference between the two. So that's the error that would be incorporated into the observed data simply because you did the wrong thing with processing the data, and inverted that to see what difference it made in terms of the densities. And rather than trying to plot it up in 3D, just average that over the top 400 metres of the inversion model, and then just looked at the differences in densities that introduced. And so these are gone too far. So these are plotted again on a uniform scale, minus 0.1 gram per cc to plus 0.1 gram per cc. So you can see most of it is green. Most of it you wouldn't even notice in terms of 0.1 grams per cc is pretty negligible. But you can see that there are systematic things coming in, and if we actually look at those, they're actually going up to 0.2 grams per cc errors, and that's over the top 400 metres of the inversion model. So certainly the using the point correction of the terrain as opposed to the integrated, you can introduce systematic errors that are related to the topography that will impact on the interpretation of the geology from the observed data itself. So you certainly do need to take into account. And you see that there's really not much difference whether you're 14 metres or 80 metres. The structures are pretty much the same in terms of the density ranges that are introduced. So what does it mean in terms of real data? Well, we've got the Falcon data for the RJ Smith test range, and we're calling it Kerrang on the slide. So these are the observed GNE and GUV responses. You can see the amplitudes pretty much the same as the modelled responses that we saw before. These are the terrain-corrected Fourier 2.67 results for the Falcon survey. And so we just applied a standard inversion process, minimising the usual objective function where you're doing the point evaluation of the observed data at the observed data locations using a particular density model. And there's the isosurface of 0.05 grams per cc. I'm guessing it could be 0.1. So it's a pretty normal standard 3D inversion, but we can incorporate, and there's the errors in terms of the achieved misfit. So you can see that there's the actual differences between the observed and predicted data on a scale -1 to 1 ERTVOS, and there's as a percentage, and you can see that there's some line effects going on that obviously in terms of the two components there's some inconsistency in the processing. Now we can modify the inversion process to incorporate the low pass filter, in this case a spatial integration filter, into, so you do the normal, you've got your model, you do your forward calculation with the standard matrix calculation in the UBC type environment, and then you apply a spatial filter to it, the spatial integration filter. So that's incorporated into the actual inversion process itself. And you can see that if we compare so that's the inversion model that we generated. In terms of the misfit errors, you can see that there's some structure in terms of the -1 to 1 ERTVOS at the edges, and that's simply because the line integration doesn't have information outside the data space, so the approximation at the edges infiltrates into the edges of the inversion errors. And the structure of the actual percentage errors is slightly a greater variation than there was with the point samples. So the point samples can vary much more quickly because the integrated samples, obviously there's a smoothing process involved in taking the point samples and generating the integrated values to compare to the observed data values. So if we compare the two, you can see that just as in the sorry, there's something I forgot. There's the green one is the normal integration using point samples, and the yellow one is the inversion using the incorporation of long line integration in the inversion process itself. And so when you compare them, you can see that there's it's got shallower depth extent, there's slightly narrower, and there's also more shallow expression of the density. So you can see that there are definite effects of incorporating, that if you don't incorporate the same processing that's applied to your data, to the data that you're inverting, then you can improve the inversion if you do incorporate the same processing that is being applied to the data. So we've got shallower and sharper anomalous mass features. In conclusion, the spatial averaging has been implemented in the inversion process. One thing in terms of the observed Falcon data, it's been filtered with a 2D Fourier domain Butterworth low-pass filter, and it's a similar effect to the spatial integration, but it's not interchangeable. So I've had to approximate it by a 3-second time integration, and by comparing the filtering effects, that was deemed to be similar in total effect. So in terms of the final, airborne gravity gradiometer data is collected over a finite time window and recorded as one value, and that value is representative of the gravity gradient within that time window, and the time window is significant in most cases. The forward modelling should also incorporate this, because it's not a discrete point, and the effect of even in mild terrain at reasonable clearances can be up to 60 ERTVOS just in the terrain correction, and it also has an impact in the inversion process. So that's pretty much it.
Thanks, John. Can I ask our presenters to come up here to have a bit of a Q&A session? We're running... All two of you. So any
Mark, I have a question for you. I'm curious. Is any thoughts put forward of using GPU instead of CPU, real-time FFT and equivalent source calculations?
Yes, that's right. So, to be honest with you, I can't, well, not so much GPUs, but we do use multiple cores in our data processing. But we use it for all of the processing that takes any significant time. We use multi-core computers.
So you see no any
So you,
advantage of...
so you do see an advantage, but I mean the advantage accrues to all of the processing methods.
Right. Okay, thank you.
Hi Mark, Matt Zenger from Gondwana Geoscience. Question for you, just regarding your Fourier and your equivalent source presentation. So just bearing those two types of things that you explained in mind, what is the sort of strategy you might employ then when, if you're say merging data sets together and they come over different types of terrain, so low and high terrain, and you've flown one with one survey, type of survey, and one with another. Which is the strategy you think is best employed?
So it depends, but I guess, if you're flying a survey in the lowlands, then you go up into the Owen Stanley Ranges in PNG and you're in a helicopter, so you're terrain following, and you want it all integrated into one package, then we'd be using equivalent source for that job. Because the advantage of equivalent source in the rugged terrain is much bigger than the...
Any other questions?
David Pratt, Tensor Research. Mark, it was a very interesting presentation, the comparison. It's the first time I've seen anything like that for the reconstitution using the Fourier domain and the equivalent source. What I'm interested in is the longer wavelength variations that you showed from the modelling and the processing. They were for the GDD component of it, and 2, I think, out of the 4 areas showed a substantial gradient in the GDD. How did that translate to GD? And any comments on how you might remove that in conventional processing for both GDD and GD?
Yeah, so there's a couple of answers to that. So first of all, yes, that effect becomes more dominant in GD, where the longer wavelengths are more important. So you can see it in the GDD. It's going to be a bigger effect in the GD. How we deal with that is, I guess, there's 2 answers really. One is, as I said in the presentation, is that our general processing method is to use gravimetry data to enhance the long wavelengths in the data. So that might be, somewhere like Australia or Canada, the regional ground gravity data sets that are available are fantastic. They're easily good enough for that purpose. But in other places it might be the S-grav system that Chris was talking about, or in the satellite gravimetry, which in many places of the world nowadays is quite good. And we're talking here at wavelengths of, for the satellite gravity, you'd be talking at wavelengths of 30 kilometres or more. Yeah. Now the other approach is if you're doing a survey, where somebody's looking for shallow, small targets, diamond exploration, for example. They're not interested in the long wavelengths. They don't really care to go and collect or have long wavelength data in there, and we just filter that long wavelength from the data before we process it. So we're filtering out wavelengths that are longer than the survey area in that situation.
Petroleum exploration, the long wavelengths, of course.
Petroleum exploration, the long wavelengths are absolutely important, so you would definitely be conforming external gravity into the data. Yeah. And that's been routine processing for many years now in Falcon data.
Any other questions? Des? How many stations of the with constant test range?
Was I paying attention? No question about the test range. James issued a challenge, a couple of things, and Mark did too. So I've got to try and turn this into a question. So James's question was, you've made a point in passing, is there a more effective way, or is there a Fourier transform that treats the tensor as a whole? I think you said that. That was one of your questions, or you're questing, or you're indicating that, I believe. I think you asked that question. Am I right?
I don't think I did, but... for sure, it's a good question.
Yeah, no, well, it's, I mean, of course, it's a quest. So we invented the inversion, the invariant transform, and then with the quest of trying to get the number of operations to do the Fourier transform down from 5 to, say, 3. And does that work? So I guess I still assume that no one else in the world has tried that yet. So have you tried that? You know, look at playing with the invariants and doing the transforms on the invariants and the rotations.
Certainly played with invariants, but not in terms of
this whole methodology thing.
Processing side of things, on the interpretation side, but not processing.
Yeah. So we have some hidden away research which demonstrates that there's some very interesting areas there. So I won't say any more. The other point that Mark was making, just as another one as a teaser, you've got the equivalent source and you've got the standard Fourier transform. Is there something in between? Have you considered there might be a method that sits between the two? How's that for a question?
Yes, so there's probably a couple of things to say there. So firstly, you know, we actually at one stage, it's going back a while now, but you know, back in the early 2000s, I guess, Guimin Liu, who some of you will know, developed a spatial domain transform method. But in practice, that did not work as well as the other two methods in any circumstance. It wasn't appalling, but it just wasn't quite as good. So that's one approach that we've taken, and you know, you could potentially do more work in that area. Right? I'm not saying that's a dead area. We had 3 methods, and we chose to keep the best 2, rather than develop more time in that one. Now, more directed at your question, one of the things we have played with to some extent is using the Fourier transform solution as a constraint on the inversion. Okay, so use it as a reference model or a starting model, or let's say a reference model would be more appropriate. And that works, but it doesn't give you any particular advantage, really. Didn't really save in processing time particularly. It saves you sort of like one iteration right at the beginning, and that's kind of it. Maybe there are other ideas in that area. It's a good question, but we have played a little bit around that part of it.
I've got a question. Question to Mark. So downward continuation is known to be undesirable. What I don't know is how undesirable is it to ignore the assumption that the upward continuation needs to be to a horizontal plane. So if you do if you do all of the transformations except the downward continuation, essentially.
Yeah, so the software in fact has that optionality built into it. So we can pretend that the data was on a horizontal surface and which is exactly what everybody does, for example, with magnetic data, with reductions of poles, whatever. We just pretend that it's on a horizontal surface, do the transform, and we're as happy as can be. And there have been some studies that I know of with magnetic data that shows that actually the errors in ignoring that can be quite extreme. Dave nodding his head. And So with magnetic data, you know, you kind of have this advantage that very often, especially in minerals exploration, the dynamic range of the signal is huge. You know, you're going to have hundreds of nanoteslas with a noise of, I don't know, 0.0 something. So you've got a huge signal-to-noise ratio. So if you're looking at a map to do an interpretation and you do this reduction pole and pretend that it's on a flat surface even though it's not, and you end up with a 40 nanotesla result, nanotesla error, you don't really care that much. I mean, maybe you should, and if you're going to use that data in an inversion, then you've made a mistake. Right? But with gravity data, you don't get that range. You know, signals in gravity gradients are tens of ETVOS if you're lucky, and your noise level is kind of a few, so you can't afford to be making 10 ETVOS, 20 ETVOS errors in your data processing. The errors in your data processing have got to be down at the instrument noise level. You know, they've got to be small. So, so you have to be very careful about that. Now, it is the case that, you know, if you're flying a survey in very flat terrain, then ignoring the upward continuation, downward continuation doesn't really make any noticeable difference. So,
I should say that I didn't talk about it in the talk, but in the paper that goes with this, I do talk something about how we do that in our belt geospace processing. And we do it without downward continuation. We put the Fourier layer below the data and iteratively come towards the correct solution. So that's in the paper, but you can read that later.
Any other questions?
Asbjørn Christensen from Nordic Geoscience. This is a question for James.
Yeah.
James, excellent presentation. I really like what you're doing at the looking at these alternate ways of using the tensor components to get to one particular component. However, I saw you had a slide, and in your analysis you also point out, or you ascertain that the Falcon system has, well, the FTG system has how many outputs? Six outputs,
but
yes.
there's one redundant.
Yeah, so there's one that's redundant.
5
yeah.
channels of information, 6
Mhm.
outputs.
Yes, plenty of information.
Yeah.
And you mentioned that the Falcon system has 2 outputs. But I saw in the presentation from Mark that he mentioned there's actually 4 outputs
Yeah, you
coming
could say
out
4
because
outputs
there's a complement, 2 complements on that system. Have you taken that into account?
Yeah, that was taken into account.
That's good.
I mean, I could have said 4 outputs and...
Okay, so there's a square root 2 in there somewhere in your calculations.
No, that was all taken into account.
Okay, all right, thank you.
Lucky we didn't have 32 by 9 presentations already. Anyone else? Questions?
I'd take a few minutes.
All right.
Craig Anderson, sorry, CGG. A question for James. Have you flown Carring to date? And is there any results?
Yeah, we have flown it, but not. It's still a partial result. We haven't.
Anyone else?
Des, you had a question?
Would anyone care to talk about gridding and the importance in all of this? And padding? Gridding and padding, yeah, right.
James is the gradient specialist.
Abject silence. Well, it's a trap.
Yeah, I don't believe in gridding at all. I don't believe in it.
But what else are you going to do?
There's no such thing.
Right. Take your measured data and invert it.
Yeah, that's what I'm saying. Why grid when you can invert and look at your density? That's what people want to see. They don't want to see gradients. They want to see density. So, in the future, there'll be no gridding.
All right. Now, we will shortly be going outside, and 20 or so minutes that we've got up our sleeves will be an opportunity for everyone to go out to view the posters. The poster presenters will be there, I hope, to be able to explain or answer your questions.
Perhaps if I can shorten, unfortunately, the time that's allotted for posters, just to get some feedback on some ideas that the experienced audience might be able to provide to me in such perfect circumstances. What I'd like to do is just take a few minutes to talk about the current situation with Geoscience Australia and the state and territory geoscience organisations with respect to airborne gravity and airborne gravity gradiometry acquisition and what role we have in that particular game. So what I'd like to do, if I've got a few minutes, is to give some background on a set of questions and then throw those questions onto the floor to get some much needed feedback for me to shape the way we move forward with these data acquisition programs. In the government organisations, we're in the business of providing fundamental data like gravity, but over large areas. We can see that the large areas necessitates stitching of multiple acquisition campaigns together to form composites. For the commodity data types, and by those I mean we no longer talk about somebody having a different type of magnetic data acquisition system to the other type. They're all vanilla flavoured. Radiometrics, more or less so, and vertical gravity from ground observations we might also describe as a commodity data type. But even there, I'd raise the point that we're seeing issues when we try to combine different ground gravity campaigns into a single data set due to their different accuracies and uncertainties. They already look a bit odd when you try to combine them. Some of the, when we combine data sets from multiple acquisition campaigns into a single composite, we're assuming that they're all measured to one data standard at some point in time, and that it's viable to combine them, to mesh them. And this is taken to be the gravity datum in the majority of situations. So just some background on the situation where we have it in Australia at the moment to the current gravity datum. It all goes back to a half dozen or so, or 5, early absolute gravity determinations that were made in key centres around Australia, and a number of supplementary relative gravimeter measurements. And those enabled Australia's gravity to be tied into the global IGSN 71 gravity datum. This was expanded then by Australia to more locations across the continent, to approximately 250 of them, that form the Australian Fundamental Gravity Network, or AFGN. The next stage was to use those to link in a base 11 kilometre coverage of ground gravity stations that were barometrically height controlled. So they have several milligauss of uncertainty around them. Since then, they've been built up by successive campaigns of government and exploration surveys, primarily using GPS as the location controls. And all of these have been linked to that same fundamental gravity network
and the estimated uncertainties of these are better than 0.1 milligauss perhaps. And most recently we've been undertaking a campaign to refresh some of the fundamental sites using a mobile absolute gravimeter, so we have a much better handle on absolute gravity at more than 100 of such sites. And this in fact led to the definition of the latest gravity datum for Australia in 2007. That is a combination of the one that we use for IGSN 71 and an absolute gravity datum, and we found that we had to shift them by the previous datum just in the straight level sense by 78 micrometres per second squared. That was sufficient to bring it into alignment. So the current situation across Australia, in some places, some jurisdictions like Victoria, nice small state, they have an existing coverage of maybe 1 to 2 kilometre ground gravity spacing. Large parts of South Australia, 5 kilometres. People from the audience can object to any of these statements if they're grossly in error at about this point in time. There are certain key regions around Kalgoorlie, Mount Isa, places like that where we have 1, maybe 2 kilometre ground gravity coverage, flanking out to 4 kilometres, but there are still large areas that still only have the 7 to 11 kilometre base coverage out there. For the last umpteen years that I've been aware of it, the primary tactic by the government organisations is to just continue to acquire ground gravity data to infill these situations. But I think it's fairly easy to look at that and see that not within 100 years are we radically going to impact the overall coverage of such a large area, just plugging away on the ground at the current rate. So we need, and in the current situation, we're just looking at individual cases on a case-by-case situation as to whether we use airborne gravity and airborne gravity gradiometry. Situations arise when it's just simply not possible to get land access into areas. Then we swap over to considering airborne data sets, but they're not the primary focus and they're not systematically pursued at the moment with the consideration of producing a coherent data set that we can put together at any one point in time. So I'd ask people, should we make the change now to solely doing airborne acquisition and spend some time looking at the issues about how we set that up so that it's best planned to be coherent, because I can see plenty of things going wrong trying to stick together airborne data sets from different campaigns and data sets from different instruments. There's many cases of shades of grey and having to make decisions that won't be agreeable to everybody. I could take the extreme case on that and say that should we consider the ground vertical gravity, airborne gravity itself, and airborne gravity gradiometry as 3 completely separate data types that should never be mixed together, that their characteristics are so completely different that it's ludicrous and distracting to even attempt to join them together. Take them as one as magnetics, one as radiometrics and one as EM, and you don't mix them together, that sort of level. When I'm done here, I'd ask, does anybody have any experience of combining many of these data sets into a regional compilation, and what was some of the fun and games and experience that was had when that was done? Methods for tying into the datums so that they're all consistent. At one end of it, you can use a completely implicit method and just fairly randomly adjust the levels so that they all level up. And the other end is to go to a lot of trouble of tying into a fundamental gravity location with a relative meter, carry that tying to a spot on the airport tarmac where the aircraft is parked, and then tying that as close as one can get into the instrument bay within the aircraft so that you can get as best possible direct tie for all the surveys, noting that each one of them is a relative gravimetry survey, not an absolute. Does that method make sense? Does it add value to the implicit method of just levelling them? When we're providing integrated data products, this was something that we just flashed across with downward continuation just before. And continuation. The current ground gravity data is delivered on the ground surface. That's where it applies to, so that if you invert it, that's what you invert it to. Now, what surface should we deliver the data to when we've got airborne data? Should we upward continue all the ground gravity if we're combining that into that coverage up to the level of the airborne survey? And what surface does the airborne data apply to? If we've produced a nice, smooth, levelled airborne data set, it's definitely not applying to the actual drape of the survey, which is not a smooth surface, and the data set shouldn't have a smooth image as the output. So it's some smoothed drape, and should we pay more attention to what that actually is? Or even go down some of the routes where we were talking about the role of models as outputs, where that can be managed. Should we go as far as delivering the equivalent source product as the product, not a data type? Deliver an equivalent source model and say, help yourself calculate it whatever surface you desire. Should that be the best way forward? And then how should we set up our data delivery services? At present, you just dial into GA, go into the gravity database, extract your points, and you get a download. With all these different options and more data types and pre-processing that's required, I can only see that we're going to have a more flexible data delivery in the future, where we provide users with options of which data sets they want, which data types they want, how to combine them. Do you have a specific drape surface that you want it output to? There's questioned some of the correction methods, the terrain corrections. Which terrain correction methodology do you want applied? Do you want a global terrain method or a Bugay one that stops dead at 167 kilometres? What of the many variants of all of those do you want? So, one more. Is an acquisition program predicated on widely spaced lines viable? Or is that something that the government shouldn't be pursuing here? Does that have no sense at all if we're talking gradiometry to supply gradient data on widely spaced lines several kilometres apart? Is that nonsensical?
That's not nonsensical.
Oh, I'm glad there was a rapid answer on that.
Particularly if you want to get a measure of how much cover is stopping us explorers finding more deposits.
A la the current Airborne EM, which gives you a taste of what's going on, whether more detailed EM is viable in an area.
I can only think that AGG can add to that equation.
So, my questions were, do we need more gravity at all? Should the government's focus on more ground measurements, or cut our losses now and go full bore on airborne data acquisitions? Should we consider the three data types, ground, airborne gravity and gravity gradiometry, completely differently? Are there spatial bandwidths and noise characteristics so completely different that we shouldn't combine them? Does anybody have experience of trying to do this and saying no, no, or yes, yes, it is viable, or no, it's not? On what surfaces should we think about providing the data, and what types of processing do we need to start putting in place to make sure that we're actually doing that in a rigorous fashion? And what should our on-demand menu-based service for delivering data look like? So, some questions there. Open to the floor.
Sounds like you're going to send us a questionnaire that we're all going to fill out. Thanks, Richard.